today we're going to be talking about a specific experiment. So when we're testing for a difference in standard deviations, we're going to compare the standard deviations of an athlete's performances in two different contexts. The first thing that we need to do is to conduct a hypothesis test to determine a hypothesis test to determine if the differences in the observed standard deviations provides convincing evidence that there really is a difference in the athlete's true standard deviation. So the observed standard deviation is what actually happens, and the true standard deviation is what is actually true. So an athlete's true standard deviation in a particular context would be the standard deviation of an infinite number of performances. So the true standard deviation is what would happen if he had an infinite number of tries. So because we cannot observe an infinite number of performances, and because the performances we can observe are affected by random chance, the observed standard deviation in a particular context is just an estimate of the athlete's true standard deviation. So if we look at this graph, you can see after many observations, the observed standard deviation will get really, really close to the true standard deviation. So that means the more trials we add, the closer and closer we're getting to a true number. The graph below, or this way, so this graph shows the standard deviation of Michael Jordan's points scored that is recalculated after each game of his during his 1978 and 1988 season. So if you look, most of the time standard deviation is going to start off with these little big jumps, and then as more trials you add, they kind of start to flatline. Well, this flat line is getting closer and closer and closer to the true standard deviation. So it says after scoring 36 points and 29 points in his first two games, Michael Jordan's standard deviation was 4.95 points. After 3 games, it was 3.61 points. And by his 82nd game, Michael Jordan's observed standard deviation was 8.58 points. If he would continue to play indefinitely, his true standard deviation would probably end up pretty close, but not exactly equal to, his final observed standard deviation of 8.58. And if you're wondering where we got this number from, is on the last trial, which was about right here. If I go back to my chart, it's going to be probably about 8 point something. That's where the number came from. So in our experiment that we're going to look at, we're dealing with a guy named Mike. Mike plays golf. We want to know which 7-iron that Mike uses is more consistent. So Mike is a member of his high school golf team and is considering buying a new 7-iron. which is a golf club, hoping that it will make his shots be more consistent. Mike decides to conduct an experiment. He will use his current 7-iron and borrow a teammate's new 7-iron to see which of the two clubs make the distance he hits the 7-iron less variable, which means less spread out. In this experiment, the explanatory variable is going to be his clubs. New and current. So remember, the explanatory variable is what are you changing with each trial. So in this one is the types of clubs. And the response variable is going to be the distance he drives the ball. So what are we measuring? We're measuring how far he can hit the ball. During this experiment, he will use control by keeping the ball, his gloves, and his shoes the same. While he uses both irons, he's going to use them at the same location. So he's not going to use two different golf courses. He's going to do the experiment all at the same time so that there's going to be no difference in the wind or other weather conditions. Because it wouldn't be fair if you went and hit a golf ball in the rain and hit one in the sunshine. It just wouldn't be fair. Because we want everything to be as fair as possible. It's also important for Mike to randomize the order in which he uses his clubs. So this is a typo. This should be clubs. If he were to hit 20 balls in total, it would be unfair to use his current 7-iron for the first 10 shots and his new 7-iron for the last 10 shots. To randomize, Mike takes 20 note cards. So here's the simulation part. He's going to take 20 note cards and write C for current 7-iron, and N, and there should only be one N on the remaining 10 to indicate the new 7-iron. So C is for current, N is for new. He shuffles and draws them one at a time to determine the club to use. It is not possible to be blind during this experiment because he'd be able to tell which club he was using. So remember, when you're being blind in an experiment, that means you don't know what treatment you're receiving. So if you look at the table, here are the distance in yards for 20 shots, current and new. And there's 10 of them each. I attached a graph of the dot plots, but just know that you should be able to draw that dot plot on your own. So if you don't know how to draw the dot plot, please let me know and I will help you. If you look at the graph, both graphs are reasonably symmetric. So they're basically all the same. If you fold it in half, they'll be the same on both sides. And they have similar centers, so that it kind of evens out. The means are about the same. However, Mike seemed to hit the ball more consistently with you have to ask yourself, which graph has the points closer together? Well, if you look at the graph, it looks like most of the points are closer together with the new 7-iron. So it looks like he's more consistent with the new 7-iron because the distances for the new club varies less from their mean than the distance with the current club that varies from their mean. So if my mean is maybe somewhere around here for both numbers, my standard deviation for this one, for the bottom, is going to be somewhere right here to here, while the standard deviation for the top is up here, close. Remember, the bigger the standard deviation is, the less consistent they are. The standard deviation with the current club is 13.56 yards. And with the new club, the standard deviation is only 7.72 yards. The difference being, if you subtract them, is 5.84 yards. So let's state our hypothesis. When you're stating a hypothesis dealing with standard deviation, you're going to be talking about the true standard deviation, okay? The null hypothesis is still going to be the same, while the alternative hypothesis is having one's better than the other. So for our null hypothesis, you're going to say that Mike's true standard deviation is the same with both clubs. So the alternative one is where we think one's going to be better than the other. So the alternative is going to be that Mike's true standard deviation is smaller with the new club than the old club. So when I made this statement that the standard deviation is smaller with the new club, that means that we think it's going to be better, that he's going to do better with the new club, because the smaller standard deviation, the better. Okay, you know how to calculate the deviations with from the mean. All you're going to do is do the performance minus the mean. So I'm going to let you fill out these two charts. You're going to do the deviations with the current and deviations with the new mean and put them in this table. Okay, I'm going to let you do that. And you're going to use these points. Okay, so do that on your own. So to conduct a simulation, you're going to write each of the 12 different deviations on a note card. Once you write them on a note card, you're going to shuffle them and divide them into two piles of 10 cards. After you do that, you're going to find the standard deviation of each pile and then subtract to calculate the simulated differences in deviations. Here are the results of 100 trials of the simulation. And that didn't get put on. So, since the dot plot didn't get put on the paper, if you go to page 241 in your textbook, so page 241 in the textbook, once you look at the dot plot, you can tell that because our observed difference was 5.84, which we got from this number. This is where we got that number from. Only 3 of the trials produced a difference in the standard deviations of 5.84 yards or greater. Because there's only 3, you would do 3 divided by 100, which gives you 0.03, which is 3%. So the p-value is approximately 3%. So assuming that Mike's true standard deviations are the same, there is about a 3% chance that he would get a difference in observed standard deviations of 5.84 yards or more by random chance. Because the p-value is small, we are going to reject the null hypothesis that the true standard deviations are the same with each club. Because you reject the null hypothesis, that means that your alternative hypothesis is true. If you look at this, these sentences will give you some of the key stuff you're going to need to know. This sentence right here is your interpretation. When it asks for you to interpret the p-value, they want you to say this. This sentence to here is the make a conclusion part of your data. So when it asks for you to interpret the p-value, it wants the sentence that is outlined in blue. When it wants you to make a conclusion, it wants you to use the sentence outlined in red. If you have any questions, please let me know. Also, if you need to pause the video and go back, you can. I need to see this paper when you finish with all of the stuff filled out.